Welcome to Chapter 9, Energy Transmission. This chapter is about how energy moves from one location to another, either through waves or through other places. We're going to talk about sound, we're going to talk about the electromagnetic spectrum, and we're also going to talk about light. What we're seeing here is a jet engine breaking the speed of sound, and this sonic boom that you're looking at there is a visual representation of that occurrence. So let's move on. We want to talk about waves in this event, in this video, so let's have a look and see where we are. Okay, so there's two different types of waves. There's two different types of waves. There are transverse waves, and transverse waves move up and down, just like a wave in a pond. All right, they move up and down, just like waves in a pond. Now, the important thing about transverse waves is that, of course, if you look at this bit of the spring, that bit of the spring doesn't physically move in the direction of energy transfer. It doesn't physically move in this direction. It actually just goes up and down. This bit of spring, this goes up and down, but that adds energy to this bit of string, which moves it up and down, and this bit of spring, which moves it up and down, and that would, etc., 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 and that allows the energy to transfer from one place to another. So although that bit of metal on the spring doesn't have a lateral movement across this way, it does transfer the energy. So it's not like the matter is moving, it's the energy is being transferred from this piece of spring all the way in a wave-like motion to this piece of spring. The second type of wave we're going to discuss is what's called a compression wave, C-O-M, compression. Are there two S's? Yes, there are. Compression wave. All right. Now, with the compression wave, what we have is, imagine a spring being pulled apart and then kind of flinging back into each other. So at some points, the springs are closer together, and at other points, they're farther apart. So this is the energy moving in closer towards each other, and the energy kind of moving far apart. Now, there's two very important terms here we need to remember on the compression waves. This is the compression, and this is what's called rarefaction. That's a bit of a weird word that we don't use in everyday language, so it's one that you're going to have to try to remember, the good use of Quizlet. So rarefaction is where the energy transfer is more separate, and this is where those particles are closer together. Okay, the rarefaction is where the particles, or in this case the spring, is farther apart, and the compression is where they're compressed in close to each other. Okay, so an example of this is sound energy. So imagine you had a ruler out on the bench and you gave it a whack, and then what would be happening to the air particles is it would be going through a cycle, I suppose, of rarefaction, compression, rarefaction, compression, rarefaction, compression. Compression, rarefaction, compression, rarefaction, and it's that vibration of rarefaction and compression that creates the sound that we hear. Okay, so this is two different types of waves that we're looking at here. This is the transverse wave, and this is the compression wave, all right? And sometimes this is referred to as the water wave, I suppose. Now, what's interesting about this, I suppose, is what we can look at this, is that often sound waves, despite being, compression or rarefaction waves, are often represented in the same kind of sine wave type scenario where a line moves up and down, and the ups are referring to the compression and the downs are the rarefaction. Okay, so you can actually represent both, water and sound, or both transverse or compression, using this style of line moving up and down. So there's a few very important terms that we need to learn here. First one is wavelength. So this is the distance between either the rarefactions or the compressions. So it's this distance here, or it's either this distance from the two rarefactions, or, which is exactly the same, the distance between the two compressions. All right. Now, so that's wavelength. You might have heard about that. The second is amplitude. So the amplitude, for a technical definition, is basically the maximum distance that each particle moves away from its usual resting position. So, in the case of water, all right. So imagine this is the level of water. If it was a calm pond, we dropped a rock in it, and as a result of the rock dropping, we had waves kind of occurring. So normally the water particle would be here, but now it's all the way up here. So this is the amplitude. Normally the water particle would be here, but it's dropped all the way down there. So that's the amplitude. And again, these should be the same if physics works. Now it works the same way in sound. I mean, if we had a completely quiet room, these air particles would be evenly distributed. All right. But seeing as we've whacked that ruler, we've had these waves of rarefaction and compression, and what we're looking at here, the amplitude, is, well, normally it's evenly distributed. So what is the maximum distance that each particle moves away from its usual resting position? Well, its normal resting position is equally distributed, and now we can measure how compressed it is here. All right, we can measure the compression here, we can measure the rarefaction here, and that would be your amplitude. Okay, so that's a quick and easy first video. So what I'd like you to do, first of all, is I'd like you to take all the blue words from Quizlet and take all the blue words from Chapter 9.1, put them into Quizlet, and in addition, because I'm a bit worried about how much you guys are doing your homework, I want you to answer questions 1 to 6 in this case. So I want you to answer questions 1 to 6, and I want you to put the blue words into Quizlet, and I'll be checking the blue words in class. Anyway, good luck, have fun, and I'll see you in class.